Welcome to the Department of Meteorology and Climate Science, KNUST. The department primarily trains students and conducts research in atmospheric and climate sciences. This significantly impacts on the socio-economical growth and development and contributes to achieving the United Nations Sustainable Development Goals.
Undergraduate project preparation and presentation, both oral and poster, are integral components of the departmental curriculum.
From 26 to 27 September 2022, final year undergraduate students presented aspects of their project work, comprising a host of high-impact and socio-economically relevant research.
The top 5 groups have been highlighted here. Stay tuned and enjoy the excellent findings and observation of these research works.
Thank you.
So hi, my name is Akwasi, a 4th year student of the Department of Meteorology and Climate Science. The aim of our study is to project near future changes in consecutive weathers over Ghana using the IPCC's RCP 4.5 future scenario. Developing countries, like our area of study Ghana, are generally considered more vulnerable to climate change. This is because they have lower capacity of adaptation. On the 3rd of June 2015, there was a flood disaster in Accra, a city in Ghana. There were a lot of factors that resulted in this disastrous event. Notable amongst them was consecutive wet days, which is calculated as the maximum number of consecutive days with precipitation of at least 1 millimeter. When these occurrences happen, or when floods occur, it leads to and destroys infrastructure and properties. Also, people living in flood-prone areas are at risk of contracting diseases like cholera and malaria. When there is an increase or decrease in CWD or consecutive wet days, it can affect food production. That is why there is a need for us to use models with sufficient accuracy to project changes in consecutive wet days in the near future.
Moving on to our table of data, we have our GPCC data, which has a resolution of 1 degree by 1 degree from the years 1986-2005. And our model, MPI ESM-MR, which has a resolution of 1.8 by 2.5 degrees from the years 1986-2005 and 2030-2039. Last, we have no ESM-M1M, which has a resolution of 1.8 degree by 2.5 degree from the years 1986-2005 and 2030-2040. Our GPCC observational data was downloaded from the years 1986-2005 from the website Derick website, and our precipitation data for periods 1986-2005 and 2030-2049 was downloaded for the models MPI ESM-M1M. CWD was also calculated as the maximum number of consecutive wet days greater than 1 millimeter in a year. Thank you.
And I'm Christabel, Oderso. So before we make our projections, we need to assess the performance of the models. So we did that by calculating the bias in the models in respect to the GPCC observational data set. And the bias for MPI ESM indicates a slight overestimation of the GPCC observational data set, while non-ESM indicates a high overestimation of the GPCC data set. So to make our projections, we use the climate change signal to do that. And MPI ESM-MR projects CWD to decrease by 4 days, whilst non-ESM projects CWD to decrease by 5 days. And we use the trend analysis method to depict how CWD is decreasing over the period 1986 to 2049. So we want to conclude non-ESM to highly overestimate the GPCC observational data set, while MPI ESM slightly overestimates the GPCC observational data set. So from our study, CWD is projected to decrease over Ghana using the IPCC's RCP 4.5 future scenario. And this projected decrease may influence food production in the near future. So because of this, we want to advise stakeholders and policymakers to provide adaptive agricultural measures such as irrigation facilities to mitigate the chances of low crop yield in the near future. Thank you very much.
I'm Derick and I'm Derick with the Zerubbabel. The aim of our study is to make far future projection the changes in consecutive wet days over Ghana using IPCC's RCP 8.5 future scenario. Consecutive wet days refers to the maximum number of consecutive days with at least 1 millimeter of daily precipitation. This climate index is a measure of precipitation with high values corresponding to high chance of flooding. We all know the impact of flooding on our society, very devastating, causes loss of life and property, and can completely ruin crop productivities. So knowing appropriate information about the far future changes in consecutive wet days can help policymakers put down the necessary measures in order to prevent such incidents. Our specific objectives are to 1. Evaluate the performance of the 275 models using the IPCC as reference data set, and 2. To project the far future change, project the far future consecutive wet days over Ghana using the RCP 8.5 future scenario, and 3. To determine the far future changes in the consecutive wet days over Ghana using the present day as base period.
This table shows the data each resolution in the period used for this work, and the method used was both the observational data and the model data were downloaded. Also, the period and models were selected using CD. The consecutive wet days was also computed to check the maximum number of consecutive wet days with at least 1 millimeter daily precipitation. Also, the models were assessed using the bias method by subtracting the observed data from the model data, and the climate change signal was also calculated by subtracting the historical model data from the future model data.
This is our result of discussion. The one shows the CW computed for the CPCC data with a mean value of 22 days, maximum value of 59 days, which is concentrated over the eastern and northeastern part of Ghana, and the minimum value of 11 days, which is concentrated at the Akwasi region of Ghana. The figure 2 and figure 2 shows the bias computed for the model, which is used for the evaluation of the model using the GPCC as a reference data. For the norm model, we had a positive absolute bias with a mean value of 163 days, and for the MPI, we had a positive absolute bias of 9 days. The MPI slightly overestimates the reference GPC, whereas the ESM model highly overestimates the GPC reference data, which can be seen in figure 6, which is the trend analysis in CW. This is the GPC reference data, and this is the MPI historical data, which slightly overestimates the GPCC reference data. This is the ESM historical data, which highly overestimates the GPCC reference data. Figure 4 and 5 shows the climate change of the model. For the ESM, CW is projected to increase with a mean value of 9 days over Ghana, which is significant to the Appiah region of Ghana at 80% confidence level. And for the MPI, the CW is projected to decrease over Ghana with a mean value of 10 days, which is significant over the entire northern part of Ghana, some part of the forest zone and the coastal zone of Ghana at 80% confidence level. Since the MPI best simulates the GPC reference data, we conclude that CW is projected to decrease over Ghana in the far future period under the RCP 8.5 future scenario. And these projected changes will already affect fragile ecosystems and agriculture in Ghana. So we recommend that farming methods like irrigation should be adopted to reduce the effect it will have on agriculture. Thank you.
Hi, my name is Jackline from Tsitsia, a final year undergraduate student in the Department of Meteorology and Climate Science, and I'm here with
And Yeboah.
We did a study on assessing floods and drought episodes in some selected synoptic stations in Ghana using Rainfall Anomaly Index. Rainfall Anomaly Index is an index developed by Van Rood to measure the negative and positive severities in rainfall anomalies. Over the last few decades, according to the World Health Organization, 80 to 90% of the natural disasters that have happened globally are floods and droughts. Floods has resulted and affected about 3 billion people with a mortality of 58,700 and an economic loss of $114 billion. While drought has an economic loss of $124 billion. In Ghana, 52% of our population are into agriculture, and agriculture's contribution to Ghana's GDP has been decreasing over the last few decades due to these extreme weather conditions. Hence, our main objective is to assess flood and drought episodes in some selected synoptic stations in Ghana using Rainfall Anomaly Index.
So Ghana is a steady area whereby the 22 selected notifications are distributed across all the 4 agroecological zones in the country. And as part of our specific objective, we assess the spatial distribution of annual mean rainfall across the country, and also the latitudinal and longitudinal variations. And it was observed that rainfall amounts decrease as you go up the latitude. So the lower latitudes receive higher amounts of rainfall than the upper latitudes. And also, the western coast receives much rainfall than the eastern coast due to the fact that most of the nation's rainforests are situated in the western coast, and due to urbanization and industrialization on the eastern coast, there's much dryness over there. So we took precipitation data from the Global Precipitation and Climatology Center, IPCC, with spatial resolution of 0.25 by 0.25 across the domain of 1981 to 2019. So these are the RAI equations formulated by Van Roy in 1965. So in computing for the RAI, we first find the anomaly of a particular year, and this is done by subtracting the mean of the domain from the annual mean of the particular year you are finding for. So if you get a positive anomaly, you opt for the positive anomaly equation, and if you get a negative anomaly, you opt for the negative anomaly equation. So the result from the ROI computation will determine whether a particular year will be classified as extremely wet, dry, or extremely dry season due to the matching of the classification table.
So figure 3 shows the results, that is the time series, and then the kernel density estimation plot for the RAI from 1981 to 2019. And from the figure, it was evident that in 1983, the country experienced a severe drought. Also, the last decade, from 2015 to 2017, throughout the country, there has been a drought episode in all the 4 agroecological zones. Also, the kernel density estimation plot shows that there has been a shift in climate at the northern agroecological zone. In the transition zone, there were 2 peaks, one shifting towards the dry, and then the one shifting towards the wet, humid conditions. In the forest zone, we found out that the climate in the forest zone was shifting more to humid conditions. At the coast, most of the events or the conditions they were experiencing were near normal. Figure 4 shows the flood and drought count for the period of the study, that is from 1981 to 2019. We realized from the results that Mwasi in the forest zone had experienced more humid conditions than all the other stations. Salt Pond in the coast received or experienced less flood episodes compared to the other stations. For the drought events, it was evident that Tettehkour in the transition zone experienced most of the drought episodes compared to other stations. Also, when we check the coastal areas where there are always perennial flood, we found out that the results were showing that there are more drought events than flood events. As part of the specific objectives, we assessed the precipitation trend for the 4 agroecological zones, and from the results, we therefore conclude that precipitation throughout the whole country is decreasing, with the maximum magnitude at the transition zone with a magnitude of -4.348. Also, that perennial flood that the coastal region experienced every year was found out that this could be due to anthropogenic activities, but not entirely meteorological causes. Also, the climate at the north is shifting more towards dryness. Tettehkour, which is also in the transition zone, was found to be the driest of all the synoptic stations. With these results, we therefore recommend that water resource management should lay out proper guidelines to ensure water availability and sustainability for agriculture and household use. Also, natural disaster management should also ensure that they lay out proper risk management instead of risk management instead of crisis management. We also advise the Ministry of Health to also rule out proper guidelines to ensure that these drought episodes
don't cause surges in CSM, that is cerebrospinal meningitis, in the northern region, as their climate is shifting more to dryness. Thank you.
I am Gertrude, and I'm here with
Prince Maria and Zerubbabel.
Our project topic is estimation of global solar radiation from multiple meteorological variables using machine learning. To begin with, solar radiation is the Earth's main energy source emitted by the sun, which provides about 99.97% of the Earth's total energy. It is required for all life processes and also drives the dynamics of the atmosphere through the evolution of the boundary layer, cloud formation, and rainfall distribution. Solar radiation can be estimated using several empirical models on several meteorological variables. The examples of these empirical models are the Armstrong-Prescott model, the Patrick model, and the Black model. However, machine learning models tend to have greater prediction accuracy with less data required and also less errors than the empirical model.
The aim of this study is to estimate daily global solar radiation using sunshine duration, air temperature, and relative humidity using machine learning. And we are specifically establish the correlation between multiple meteorological variables and solar radiation in the Sudanese Savannah region of Ghana. And we are also to assess the performance of the machine learning model to estimate solar radiation during the rainy and dry season of the study area. Doninga is a typical grassland area which is located at latitude 10.617 degrees north and longitude minus 1.42 degrees 420 degrees west in the Upper East region of Ghana, with an elevation of 162 meters, an average rainfall of 900 millimeters, and average relative humidity of 56%. These are our model evaluation tests we used. The root mean squared, the standard deviation, and the mean bias error.
Our study period spanned from 2015 to 2019, and our data contained 4 primary meteorological variables such as the relative humidity, air temperature, sunshine duration, and solar radiation. Our data set had a few missing values which accounted for 3% of the data set, the total data, and the models for this study were developed using the random forest regression algorithm. The random forest regression algorithm is a machine learning algorithm that utilizes an ensemble learning approach to construct multiple decision trees for the training of the data in order to accomplish regression tasks. A decision tree is a tree-like model that is used to express an outcome based on a possible set of decisions. And for this study, we constructed 100 decision trees using the random forest regression algorithm and found the average for all the decision trees during training time to get our predicted values. So for our study, we used the scikit-learn library in the Python programming language, and we used 80% of the data for training and 20% of the data for testing. And we were able to construct 3 machine learning models, one with just sunshine duration, one with just air temperature, and one with a combination of sunshine duration and air temperature, in order to form a comparative study between the 3 models constructed and evaluate the performances of these models. So we could tell from the models constructed that all the models constructed were able to closely fit the daily observed solar radiation from the time series plot we have here, in the exception of sunshine duration, which had a few anomalies or outliers. And we could also see that the moving average for the observed data set was able to closely pass through all of the predicted values for the different models we constructed. Also from our regression analysis, we could see that the sunshine duration model was the model with the least performing statistical values. It had an R-square, which is the coefficient of determination of 0.55, a root mean square error of 61.44, and a mean bias error of minus 6.65. Our air temperature model also had an R-squared of 0.86, a root mean squared error of 34.75, and a mean bias error of minus 10.06. And finally, our combined model, which was constructed from both air temperature and sunshine duration, had an R-square of 0.86, a root mean squared error of 34.16, and mean bias error of minus 11.52. We could see that the sunshine duration model was the least performing model because it had the greatest root mean squared error, which denotes the distance the data points are from the line of best fit. We could also see that the combined model was the best performing model with an R squared of 0.86, a mean bias error of 34.14, a mean root mean square error of 34.16, and a mean bias error of minus 11.52. Finally, here we can see that the models we constructed were able to depict the seasonal changes in the climate, in the seasonal changes for the steady area, which is done in there. We could see that the sunshine-based model was able to tell us the regions of high solar radiation and low solar radiation, which depicts the seasons for the rainy season and the dry season, because the rainy season is characterized by cloud formations, which result in low solar radiation collected at the surface of the Earth. But we could see that the sunshine duration model performed poorly in depicting the seasonal changes, because it showed a high deficit in depicting the seasonal changes for some of the years, whereby the air temperature model and the combined model was able to closely depict the seasonal changes for both rainy and dry season for the steady area.
From this study, 3 models were successfully built using the random forest regression algorithm, which included the sunshine duration, air temperature, and the combination of the sunshine duration and the air temperature model. Among these 3 models, it was observed that the combined model, which is the combination of the sunshine duration and air temperature, had the best performing model with an R square of 0.86 and root mean squared error of 34.59 and root mean bias error of negative 10.8. Contrary to literature, our study showed that the air temperature based model had the best correlation with solar radiation, and then this solar radiation, this is attributed to the fact that our sunshine duration data was collected from a nearby station, which is 47.7 kilometers from the steady area. We therefore recommend that in the absence of sunshine duration data, using nearby climate station data should be done with caution, because it has the potential to influence the results of the study. Thank you.
My name is Tettehkour, and I'm here with Korean Esther.
Akwai Thomas.
We are working on the changes in rainfall seasonality over the savanna zone of Ghana. Rainfall is one of the major variables of climate. It plays an important role on our life on Earth. The schedule of agricultural activities for a developing country like Ghana is rainfall dependent. Rainfall helps drive most of our socio-economic activities for a developing country like Ghana. Our climate has changed, and the influence of climate change on seasonal rainfall is not known.
In order to find solutions and answers to our problem statement, we ask ourselves these questions. How much change has occurred in our current climate change in terms of onset, cessation, the length of growing season, and rainfall intensity? Our main objective is to examine the changes in rainfall onset, the cessation, the length of growing season, and rainfall intensity, and specifically determine the change in onset days, cessation days, the length of growing season, and rainfall intensity. Our study area is the savanna zone of Ghana, generally to be precise. Our data is rainfall, spatial resolution is point data, temporal resolution is daily. Our duration is from 1960 to 2020. Our source is from GMET.
So in order to analyze our data, we use cumulative percentage curve. And in this curve, we first compute the daily mean for the entire period from 1960 to 2020, covering the onset, cessation, and length of growing season. We then calculate the annual rainy days in steps of 5 days, and then we will then calculate the percentage of the 5 days intervals, and then determine the cumulative percentage. Then, according to Adekunle in 2004, suggested that the minimum and then the maximum curvature being 7% to 8% and above 90% corresponds to the onset and then cessation. And then the difference between the cessation and then the onset corresponds to the length of growing season, with the intensity being calculated as the total number of rainfall divided by the total number of rainy days. With that being fine, We then find the mean annual onset, cessation, length of growing season, and rainfall intensity for the entire period. We will then plot a graph of onset for the entire period. Then for the results, we found out that the onset days, the mean onset days start on the 105th day, and then on a calendar year, it falls on the 15th of April, with the cessation days falls on 276th day, which falls on the 3rd of October. So, and then the length of growing season, the estimated mean length of growing season was found to be 170 days, with intensity being 15.15 millimeters per day. So with that said, the conclusion, we then conclude that the mean annual onset and cessation days in the Nyendi area was found to be on the 15th of April and 3rd of October, respectively, for onset and cessation. And then the mean length of rainy season and then the intensity was found to be 170 days and then 15.15 millimeters per day. So we later found out that the seasonal rainfall is very, very highly variable, and then changes in seasonal indices does not follow a particular pattern from our studies.
We recommend that since rainfall in the savanna zone of Ghana is very difficult to forecast, we recommend more details on this mechanism driving rainfall variability.
So we also recommend that farmers should start preparation of their lands from the late of March through to the late of October.